Okay, working on areas between curves, and they got a trig integral for us. I was in such a good mood. Oh well. Here's our first curve, sine x. We know that starts at the origin, and it goes up, and it comes back down, then it goes negative, and then it comes back up. That's one period of the sine function. And then we have the cosine function, which has the same wavy shape, but it starts at a maximum, and then it drops, and it bottoms out, and it comes back up, and it peaks. It does everything that the sine function does, it's just out of phase with it by 90 degrees. So there's our two waves, and they want the area that's between the y-axis. Okay, there we go. And pi by 4 radians. I believe they're talking about this section here. The question is that intersection at pi by 4 radians? I believe it is, but let's make sure before we go on. So the question here is, where do these lines cross? Probably at pi by 4, but let's make sure. We're asking when is sine x equal to cosine x? Now, if you've got a decent memory for the trig functions, you might remember that the one place where sine and cosine have the same value is at 45 degrees, where they're both 1 over root 2, or root 2 over 2 if you prefer. So if you've got that in your head, then you already know the solution is 45 degrees or pi by 4 radians. If you happen to not know that, say you're having a bad memory day, and you have to solve this, there is a way to do it, and it helps if you can get this from two trig functions down to one. Is there any way you could combine a sine and a cosine function? Yeah, there is, and it involves dividing. We know that sine over cosine equals tangent, so here is a possibility we have. We can divide both sides of this by cosine x. And if we do, we get tan x equals 1. And we can solve that by doing second tan or arctan. That means the value of x we're looking for is inverse tangent of 1. And if you do that, you'll find either 45 degrees or pi by 4, depending what mode your calculator is in. So yes, all that to say, this little region here with its curved edges really does end right at pi by 4 rads. So good, we know that. Let's see if we can set up an integral. I should have labeled these curves. I'll do that now before we dig in. The red curve is cosine x, and the blue curve is sine x. That's going to come up in a moment when we figure out which is our top and bottom of our differential rectangles. There's an integral. What do we put in it? The tops of these rectangles, the tops of our slices that we're taking in here, are cosine x. And the bottoms, all of them end on sine x. So cosine x minus sine x will be our integrand. We have to have a dx on the bottom, or sorry, at the end. And our limits of integration are, they said to start on the y-axis, which is where x equals 0, and cut off right here at pi by 4. Okay, let's see if we can antiderivative this. The antiderivative of cosine x is easy, it's sine x. The antiderivative of negative sine x, oh, that's easy too, actually, that's cosine. We've got weirdly nice integration going on here. No need for the plus c, it would cancel even if we did put it in. And we're going from 0 to pi by 4, which I'm going to write as 45 degrees because I find it easier to think that way. So if we plug in our right-hand boundary and our left-hand boundary, we get sine 45 plus cosine 45, or if you're writing pi by 4s right now, that's perfectly fine. We should have the same answer in a moment. And here we get sine 0 plus cosine 0. Okay, sine 45 degrees is 1 over root 2, or 0.707. Cosine 45 is exactly the same amount. And then we get minus sine 0 is 0, cosine 0 is 1. So 1 over root 2 plus another 1 over root 2 is 2 over root 2. And then we get minus 1. You could stop there, I suppose. Or if you rationalize this, it'll come out to root 2 minus 1. That's definitely an improvement. I was going to find a common denominator for this, but it turns out we don't need to because it cleaned up so nicely. What I did here real fast, just in case you haven't thought about rationalizing in a bit, is I multiplied the bottom of this by root 2 and the top of it by root 2. And so I got 2 root 2 over 2. These 2's cancel, and all that remains is the root 2. So root 2 minus 1 is a nice answer. And if you did that as a decimal, it would be like 1.41 minus 1, so 0.41 if you like decimal form. And I'll give that wavy lines because really root 2 isn't exactly 1.41, but it's pretty close.